atomic structure. There is a video that I'm going to want you guys to watch, but it just doesn't really want to play on this recording, so I'll just send you the link, but it's the history of the atomic structure. So this is a really just nifty diagram, and the video is going to cover, all of these, which is really cool, and I think they have some really cool experiments. But what we're going to focus in on is your Bohr's model and your quantum model. It's kind of what we're going to deep dive in. Great. And so just as a review, we now know that there are electrons, protons, and neutrons. So protons and neutrons right here, these particles are in the nucleus, and protons have a positive charge. Neutrons are neutral, as their name suggests, but they are slightly heavier than protons, and electrons are super teeny tiny and are negatively charged. And electrons are what this whole lecture is about. So this is really the star of the show right here, is the electrons. So for Bohr's model, Bohr benefited from spectroscopy. And so spectroscopy, pretty much anytime you have new tech on the field, you are going to have new discoveries, because the new tech allows you to do things that you just weren't able to actually do beforehand. So what spectroscopy is you fill this glass tube right here full of, your elemental gas. So they put hydrogen gas in here, and then the light went through here, and then the light was passed through a prism, and the prism diffracts the light, just kind of like how rain diffracts light after it rains out, and you get a rainbow. Well, it diffracts the light, this white light that has all the colors in it for a rainbow, but for an element, it only has certain colors. And so these colors are called a banding pattern. They create this line spectrum down here, and this line spectrum, they're specific for the type of element that they tested. So this is a line spectrum for mercury, Hg. And they found that with every single type of element, you could have a different banding spectrum. You're like, oh, cool, that's awesome. Just kidding. I have no idea why I should care. Well, why you should care is that the reason why you're seeing light is because of what's happening with the electrons over here. So if you look at this diagram right here, the electron is that little blue dot, and as it's orbiting, it's going to become excited. There's going to be this energy input from the outside, and it's going to strike the electron. The electron is going to get excited, and it's going to jump up into this next energy level. And then an electron, it does not like to stay in an excited level. It wants to be closer to the nucleus. It wants to be at its ground state. And so it's going to release that energy as light. And when that light is released, that is what we're seeing on these banding patterns, this electron falling from an excited state back down to its ground state. And so the significance of each of these elements having its own banding patterns is that it means every single element has a different thing going on with its electrons. So as its specific electrons are dropping down from these excited states, it's releasing a specific type of lighting and energy. So that gave Bohr this idea that electrons, they're not just in a fixed orbit, they're actually jumping between orbitals and jumping up and then down. And guys, this is just what electrons do. They jump and then they fall back down when they're excited. Now, the incredible thing about this is that is how we see light. The movement of electrons is how we get light. And I think it's just really incredible and fascinating that the very first words out of God's mouth that's recorded in Genesis is "let there be light." And the way we get light is through electron movement. And so it's just, I think, I have no idea exactly what it all means, but I think it's really cool that these elementary particles that make up our universe are what give off light as they move, as they naturally do their thing. And it's just really cool that that was the first thing God said. So these energy levels that these electrons, that Bohr is suggesting electrons are orbiting around. So over here, your energy, your energy level diagram. Sorry, I'm trying to use this so you kind of know what I'm talking about. Your energy level diagrams, they have fixed energy levels. So kind of like a ladder. A ladder has these fixed rungs. And in your elements, your electron orbitals, the distance between these rungs are not going to be the same. And in class, I asked, why do you think that's true? Why do you think it takes an electron more energy? So there's more energy to move from this first ground state, this first energy level up to 2, basically ripping an electron from your first one up to your second one. Why would that take more energy than if you're way up here and you're way up here? Why is there less energy? Why does it require less energy to take an electron from your 7 and to go to 8 versus 1 to 2? Well, in class, someone pointed out that electrons, they're negatively charged, and your nucleus is positively charged. And so if you have a negative charge close to a positive charge, like magnets, it's going to cling very tightly. And so it's going to take a lot more energy to rip it from 1 to 2 to make it move. Whereas way up here, this negative electron is not feeling the pull from your nucleus that tightly. And so it's way easier to pull these guys out of there. So this is all important. This is your principal energy levels. It's going to be important for our understanding of just the atomic model. And we're going to move into quantum mechanics. But what the word quantum means is it just means it's a fixed energy level. It's a fixed number. And so these steps of these ladders, they are fixed. In order for an electron to move from 3 to 4 or 4 to 5, it's the same amount of energy each time it goes from 3 to 4, 3 to 4. It doesn't matter what element it's going to be, it's going to have the same amount of energy required to move from these energy levels. And so that's what quantum means. It's just a fixed number. So just to kind of help you wrap your brain around where we're moving. All right, I love this slide, mainly because I just think it's very funny. But it's also, I think, a really helpful metaphor. So we're going to think of atoms like people. So the inner organs, those are your protons and neutrons. Guys, those are extremely important. However, we're not going to mess with your inner organs, like at all. But your clothing is going to be your electrons. So the layers of clothing that you have are your energy levels. So there's space between each of those layers, just like when we look back here. Oh, that's not letting me go back. Just like we talked about, that there is space, there's this quantized energy fixed levels for your electrons to move. So that's the space in between each of your layers of clothing. And so for an atom, you have some atoms are cool with just like this one layer of clothing, and so they're pretty small. And some atoms need tons of clothing, and that means they have tons and tons of electrons, so they're bigger. Now we're going to talk about these valence electrons, these outermost, later on in the slideshow. So we're not really going to talk about that right now, but I'm just trying to help you understand, like, your electrons, they are on these layers of clothing, and these layers of clothing are your energy levels. And so not all atoms have the same number of energy levels because they don't have the same number of electrons. Okay, this is just a really cool picture, I think. So this is was taken in 1927 at the Solvay Council Conference. And it was just titled, the most intelligent photo ever taken. And so I just think it's really cool to see these people who your textbook is naming all these laws and stuff after. You have Einstein, you have Curie, you have, Pauli, Pauli exclusion principle, you have Heisenberg, you have Bohr, Schrodinger, all these guys. And so they actually came together at this conference to argue, which was like really cool. So you have Newtonian physics championed by Einstein and some of the older generation, And then the younger generation is going to bring in quantum mechanics. And it's just kind of trying to understand, how these things work. And so Einstein, right here, had had previously in earlier years, proposed that light operates both as waves and as particles. And so that really just shifted people's understanding. And so then, these younger guys, we have, like Schrodinger, Pauli, Heisenberg, and I'm not just picking on, the old guys, but these guys, they realize that, electrons also act like particles and waves, which is really important because that just kind of opens up this whole new understanding. Like, we can't just view an electron like a little particle moving around. It's also this wave. Um, and Heisenberg, I think, interestingly enough, this guy is like in his 20s, and he just wrote, a thesis, his doctoral thesis on the uncertainty principle, and we'll get into that. But him and Einstein basically argued it out, and Heisenberg, I mean, until Einstein died, like, Heisenberg was never able to actually convince Einstein of how he views and how he understands these electrons to work. But I mean, his model, it works. So I don't know. Anyway, I just think it's cool. And this timeline right here is not, it's not essential to like your exam or anything, but I think it is very helpful for understanding just how people are building on each other, how technology is helping, how things are being understood, because you can look at your textbook and just be like, oh yeah, obviously this is this. But I think this timeline just gives you perspective and appreciation for how many people and how many years went into understanding this stuff, and still how far we have to go. So Heisenberg, what he is saying is, what we observe is not nature itself, but nature exposed to our method of questioning. And so what this means is like the wave particle duality, that concept. When you do certain experiments to view electrons as particles, like, you are going to find it as a particle. When you do other experiments to see if it's a wave function, it also shows as a wave. And so it's like, you can only ask one question at a time, and that can only give you like this small glimpse into what's happening. But then if you ask a different question, you get this other small glimpse. And so it's not necessarily that nature is changing, it's just the way that we ask questions, the way that we do experimentation affects what we're going to see. So the Heisenberg uncertainty principle, what he's saying is, one cannot simultaneously determine both the position and the momentum of an electron. Meaning, if you find an electron and you're saying, okay, I want to know exactly where it is, you have to actually impact its momentum, its movement, to find where it is. So you don't actually know what its momentum is because you change that. And then vice versa. If you want to know exactly its momentum, well, to find that, you have to affect its position. So Heisenberg, he came up with this not because he was just, dreaming about stuff, but because he did very precise experiments, and his data just showed that this was true. And so with Heisenberg's uncertainty principle, then we're moving into quantum mechanics for electrons and atoms, and we're going to move into this electron cloud model. So Schrodinger, who was in that picture before, he came up with the Schrodinger equation, which, I mean, it says that he basically just woke up one morning and wrote the equation from his understanding of quantum mechanics, and it just, it works. And so we're moving away from kind of this electron orbit model, in the sense that this model is a 2D model, and it's your electrons move in these circular or elliptical paths. And in your electron cloud model, it's a 3D model, and your electrons kind of move in some crazy shapes. There's crazy shapes that the electrons could be moving in. And I just don't have like another way to say this, but like, you guys are just going to have to buckle up because this is going to get a little bit, tricky to understand. So we're going to try the best we can. So what we're going to talk about is our quantum numbers. So basically, based on Heisenberg's uncertainty principle, is we can't know for sure exactly where the electrons are in, in your atom. But we can get close. We can basically come at it from multiple angles and talk about, okay, well, what energy level is it? What's the principal energy level? What is the shape of the orbital? Like, how is the electron moving? What shape is it moving in? And then we can talk about, okay, well, what is the orientation in space that orbital is in? And then finally, what is the specific spin of that electron? And so you can think about it um, like an address. So your principal number is like your state, or sorry, your city, San Antonio. Your azimuthal uh, quantum number, the shape of the orbital, that's going to be your zip code. So we're going to narrow it down to the specific area of the city. And then your magnetic number is going to be your street address. So we know that this is on this specific street, quantum number way. It's on that street in this city, in this part of the city, on this address. And then this is going to be like a house number or an apartment number. This is going to get you close. So basically, we've kind of narrowed down where we think, to the best of our understanding, this electron is going to be. We can't know 100% for sure it's there, but we can get pretty close to understanding this. Alrighty, so we're jumping into our first quantum number, our principal quantum number. So this describes the size of the orbital. It also gives you the energy of the electron in the orbital. So this is what we are talking about over here. We are talking about this with our Bohr's model. So we already have this concept that electrons, they occupy these energy levels, 1 or K. It's just synonymous. You can either say energy level 2 or it's at shell L. And these energy levels, they 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 show you your energy. So your possible values of N are 1, 2, 3, 4, 5. It goes all the way to 6, 7. Technically, like there could be like 8 and 9, but like it's extremely unstable at that point for electrons to be there. And so we kind of top off at 7. All right, guys, if you do not have your periodic table in your hands right now, like pause the video and go get them, because we are going to talk about your periodic table a lot in these next few slides, and it's just really helpful. So your row numbers over here on the side of your periodic table, these row numbers are that first principal quantum number, your energy levels. So your periodic table is literally designed to show you your quantum numbers. The way that it's written out is to show your quantum numbers, which is great. So that means hydrogen, your first one, right here is going to be in your first energy level. So that's 1. And then so on and so forth. Now, your transition metals right here, which corresponds, to this area right here, your transition metals are going to be whatever the row number is, your principal quantum number, minus 1. And so these transition metals are at a slightly lower energy level than the ones, your metals and non-metals slash, metalloids. And then over here, this block of your periodic table, it's going to correspond over here, and that's going to be your energy level minus 2. So again, it's slightly lower. And so this block actually should be kind of right here in your periodic table. You'll see it on your periodic table. There'll be like these 2 boxes that say like, see this area to see what these elements are. And so these blocks right here, your actinide and lanthanide series, it's called that because this is called actinide, this is called lanthanide, starting down here. That's where it's taken from. So you would see this would be broken into 2 rows. And so this one right here would be the outside the period table, or sorry, your row number would be 6. And so here it would be, this first row right here would be 6 minus 2. So your energy level, all these would be on energy level 4, because 6 minus 2 is 4. And this would be 7, so that would all be 5. Okay. All right. For your next quantum number, your azimuthal quantum number, this is also called your angular momentum number. This is going to be talking about your subshells. So this first right here, this first energy level, we said, this is 1. This is our first energy level. And its subshell over here is going to be S. So a subshell it's describing both the shape of the orbital and it gives where the electron is located. So these numbers right here, for if you're at your first principal energy level, then your subshell could be 0. And 0 represents the s orbital. Now, guys, I'm not going to like hammer these numbers so much because they're a little bit confusing. What's really important is looking down here, looking at what we're talking about. So these shapes and all these numbers are coming from Schrodinger's equation and coming from these equations where when you do the math, you actually get these geometric representations, these pictures, geometric pictures of where the electron could be. So this is saying at your S, subshell, at this shape, an electron can be anywhere, most likely it will be found anywhere within this shape. It can be anywhere within this sphere. That's how the electron is going to move, anywhere within this sphere. So the sphere itself is not an electron. It's saying that the electron can be anywhere in there. And then for, your second energy level over here, our second energy level, it can have 2 subshells, so S and P. So an electron can be orbiting, as like a sphere. It can be orbiting as a sphere, or the electron can be orbiting as a dumbbell pattern. And so it's not that the electron looks like a dumbbell, it's just that an electron can be orbiting anywhere like this. So like the most likely place you'll find the electron is anywhere in these areas right here. So it's some in that area. And guys, again, these shapes, they're not just random. They're derived from these equations that talk about understanding its electrons. And then you have your S, your P, and then D. So over here, so when we move to our third energy level, you have your D, and that makes sense. Like if you look at your periodic table, you have your S, P, and then D, and we'll get more into that. And you guys can't see the periodic table, which is okay. All right, so this is for your third quantum number, your magnetic quantum number, and this is going to indicate the orientation of your subshells. So we're talking about we're moving in the Z plane, the X axis plane, and the Y axis, meaning it can go side to side, up and down, it can go come out towards you. And these orientations are going to be extremely important. So this is representing your magnetic quantum number, all of your orientations, meaning there can be basically one orientation. The 0, it's saying you can have one orientation for your S subshell. And if you think about it, it's because S is a ball. Any way you move that ball, it's going to look exactly the same. You got 1. That's what all these fancy numbers are saying. For these dumbbell shapes, you can have 1, 2, 3. It can be on the x-axis, the y-axis, and the z-axis. So we see right here, 1, -1, 0, and +1, meaning you can have 3 orientations for it. For your D subshell, you can have up to, there's 5 orbitals, you can have 5 orientations. And for 3, you can have 7 orbitals, therefore you can have these 7 different orientations that these electrons can be moving in. So we're gonna do a summary page. We're not done with our quantum numbers. We have one more to talk about. But before we talk about that, we're going to talk about our just our summary page here. This is really important to know right here. Each orbital can only hold 2 electrons. So right here, your max number of electrons per orbital is always going to be exactly the same. So in your quantum model, it's going to be 2 electrons per orbital. So that means you can have 2 in here. 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 And these shapes aren't representing the electrons. They're representing where the electron could be, and it moves in that shape. So because we know that each orbital can only contain 2 electrons, it's important because that means when we're at, our first energy level, second, third, fourth, fifth, sixth, seventh, specifically for your s orbital, because they can be at multiple energy levels, but this orbital is always going to look like a ball. Like it's always going to look like a ball, and it's always going to be able to only hold 2 electrons. Now, when you get to your p orbitals, since this can hold 2 electrons, and this can hold 2 electrons, and this orientation can hold 2 electrons, your max number of electrons for your p right here is going to be 6. That was not a great circle. So p will always be able to hold a maximum of 6 electrons. So we have 6 electrons here, we have 2 electrons here. Now, I'd like you to think about if we can hold 2 electrons per orbital, this is 2, 2, 2, 2, and 2, we have how many electrons? 10. 10 electrons. Oh, that's a terrible 10. Oh, dear. And then F, I'm not going to even try to circle all those, but we have 1, 2, 3, 4, 5, 6, 7. So there's 7 different orientations that these orbitals can be in. And so that means there's 2 electrons per orbital. So we can have a total of 14 electrons in your F blocks. Finally, for your spin quantum number, the spin quantum number indicates that 2 electrons, how we talked about every single orbital can only hold 2 electrons, those 2 electrons have to have opposite spins. And this comes from the Pauli exclusion principle. He proposed this. Pauli, as you saw in that picture, you could find him. He proposed this, and if you think about it, these electrons are both negatively charged. If you've ever held 2 negatively charged magnets close to each other, they're going to repel each other. Like electrons do not want to be next to each other. They want to be far apart. And so if 2 electrons have to, max capacity, you have these 2 electrons in this orbital, they are going to try to stay as far apart away from each other as they can. And another way to do that is by giving each other these opposite spins. This is also important because no element can have the exact same quantum numbers to it. No electron can, so this helps us define where the electrons are at. All right, for your quantum number summary chart, this is everything that we just talked about. I just think it's like a nifty page that kind of gives it all together so you can look at that. All right, guys, I'm like popping up on the screen because we're going to talk about your periodic table, and I'm going to attempt to show you with my paper. The periodic table is just really awesome because it is literally designed to show you all of your quantum numbers. Ooh, it's hard to like make sure this is like straight and not like... Okay, so your periodic table, you have over here this section right here. If you printed out the periodic table that I had on the website, it's going to have this little block, and it talks about your electron configuration block. And so this whole section of your metals right here, this is your alkali metals, alkali earth metals, and we'll get more into that. But this is your S block. So that means these elements, their electrons are all gonna move in a spherical pattern. And you can only have up to 2 electrons here. Now, I think this is really cool. If you look at your periodic table, the way it's shaped, like they could have shaped it a different way because it's just they just line it up by your protons, like adding the number of protons for each. So this has 1 proton, this has 2 protons, 3 protons, 4 protons, 5 protons, etc. And so if they're just worried about the protons, then they could have taken this right here, moved it back up to here, and then this would have been like super duper long. But they're not just worried about the protons. They're really focusing in on the electrons. And so, and specifically the quantum model. And so that's why it's shaped this way. So your S block right here, it only has 2 elements. One, and then your helium is technically part of your S block. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. This is significant because your S block can only have up to 2 electrons, right? Because you can only have 2 electrons per orbital, per your subshell, and S can only be in one orientation. Like you can only have a ball. Like you can't make it look any other kind of way. And so then we're going to come over here. Again, look down here that says your P block. So your P block, we talked about, it could hold up to 6 electrons because it's those dumbbell shapes, and the dumbbells can be on the x-axis, y-axis, and your z-axis, like coming out at you. And it can hold up to 6 electrons because of its 3 orientations. So let's count our number of elements that are in our S block. 1, 2, 3, 4, 5, 6. Holy smokes! There's 6! And it can hold 6 electrons max. Like, guys, do you see how awesome that is? Like, your periodic table is literally telling you the quantum numbers. It's saying this is your P block. It can hold up to 6 electrons based on where it is. And then your D block right here, your transition metals. That's why they took this actinide and lactonide series and just like kicked it out. They're like, you got to go because you're in the F block. You're going to do something weird and funky. So we're going to just look at these as our D block. Our D block can, it had more of like that clover shape, the flower shape, well, I guess clover, and it can hold up to 10 electrons max because it can have 5 different orientations in space, and each orientation can have 2 electrons. And so let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow, 10! It can have a max of 10 electrons, and it's got 10 elements. Like, again, this is showing you your quantum numbers. And then your actinide and lanthanide series are your F block, and they can have, there's 14 of them, and your F block can have a max of 14 electrons. And your row numbers going over, again, these represent your principal energy levels. So if we were to do your quantum numbers for hydrogen, let's just do an example. We would have 1, because that's the row number. So that's your first number. Your first quantum number is 1. And then what block is it in? It's in the S block. So then your next number would be S. So hydrogen would be 1, S. And how many electrons can it have? Well, 1, because it's the first one. 1. So 1s, 1. That would be its quantum number. And its spin, according to our chart, if you look on the slide, the chart would be plus 1/2. So if I were to ask you your quantum number for any of these, you could tell me kind of what your quantum number is. And I know you're saying, actually, I can't because I don't quite understand this. And that's fine. We'll do more practice. All right. Since my video is already up, we're gonna keep it up so you can see the face of those who torture you. We are moving into your orbital diagrams. And so this is everything we've been talking about, but in a graphical representation. So we're not changing things. We're not switching gears. We're just trying different ways of showing you what we've been talking about. And so if you look here, we were talking about the S. So our S subshell, it's a ball. Like that's just like the easiest way to picture it. There can be 2 electrons anywhere within this ball area. And so these arrows are representing the electrons. And the reason one is up and one is down is because of that 4th quantum number, that they have to have opposite spins, right? Like the electrons, if they have to be in the same orbital, they're still wanting to kind of repel each other. They're still wanting to stay kind of far away because they're negatively charged. They're both negatively charged. And so then we move into our P, SP, And P, again, is the dumbbell shape, and it can have 3 orientations. And this is showing in one orientation, you can have 2 electrons. In another orientation, you can have 2 electrons. And another electron, you can have 2 orientation. So you can have up to 6 electrons total in this second, energy level, this P, anywhere where you have this P block. You can have these orientations. So, and the same goes for D and F. And this over here, this picture right here, is just showing you, it's just talking about this, but kind of breaking it down for hopefully for you to see like, okay, look, we are in this first energy shell, and at our first energy level, we can have up to 2 electrons, and these 2 electrons are going to move within like a ball-like area. And then if we move on to our second energy level, we can have up to 8 electrons because we can have an s orbital and we can have a p orbital, 2, 6, and then so on and so forth. So we're going to talk about orbital diagrams. And for orbital diagrams, you can have, you write it out based on the energy levels. So starting on 1s, all this is saying is I'm going to, sorry, my section's like really small. That's why I'm saying, like, look at your periodic table. I'm sorry, it's got this like weird glowy thing on it. This 1s is right over here. So we're at our first row 1, and then s, this first s block, 1s, and this could be hydrogen if we would just put 1 electron in it, or it could be helium, because helium is in 1s, because it's 1, your row number, s, your p block. Sorry, helium is so tricky, but it's supposed to be, just think about it like it's right here. And then 2 electrons. Now, as we move up, as we go up our energy levels, we have hydrogen, and then lithium starts our second, and their second row lines up over here. So you move into 2s. Once those are filled up, you just follow your finger across the periodic table. You can get to P, your P section. So over here, we move up to 2p, and that can hold up to 6 electrons, and there's 6 of them. And then we come back down, and we move into our 3, and then we move across, and we hit 3p. And if we move our finger down our periodic table, we get to 4. So we have this 4s right here, which is interesting. But then, look here. This says 3d. It's like, what? I thought we just moved into 4. I thought we were just at that 4th number. Well, we are, but again, I'm just following. I'm going straight to the next block over, which is your D block. You run into your D block, and what did we say about the D block? The D block is your principal quantum number, your 4, minus 1. So it's at a lower energy. Even though it's right here, we take it to a lower energy. And so that is why this says 4s on it, and this says 3d. So we're still filling it in, but these actually go at a lower energy. And so there's this energy overlap kind of situation going on. And this sounds complicated, and it is. Like, it is complicated. And the reason we have to do this on the periodic table, the reason it can't just be like clear and simple, is because nature is not clear and simple. It's complicated. And so we're trying to represent this the best way we can. And so I think, personally, just being familiar with your periodic table makes this like pretty helpful and simple. But another tool that people have developed is this right here. So what they do is they say, okay, write out all of your, your energy level and then your orbital. So 1s in order. So 1s and then 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and so on. And you just like write it out in that order. And then you put these diagonal lines through them. And so the diagonal lines is helping you remember, I'm going to, when I'm writing out my orbital diagram, when I'm writing out my electron configuration, what I'm doing is I'm starting where my diagonal line is. I'm filling in that direction. So I start in 1s, and then 2s, and then 2p, 3s. So that's all tracking right here. And then 3p, 4s, and then I know 3D, 4P, 5S. But again, guys, all that is saying, that's just supposed to help you be able to write this out. But again, if you looked at your periodic table, all that is saying is I'm just following my periodic table just across. I'm just going straight across. I'm writing this out. But when I hit my transition metals, this block right here, my D block, I'm just remembering that this is my row number minus 1. So my energy level is just less, 1 less. So I have a feeling most of you are either tuning out or you're just like giving me like this like dead eye look, like I don't understand what you're saying. But we'll practice this, and hopefully it'll be more clear. All right. So our rules for creating orbital diagrams, we're going to talk about 3 different rules. So when we go to write out our orbital diagrams, when we go to show how much, where the electrons are. So it's not just saying how many electrons they have, we're saying where are the electrons? Okay, we know some of the electrons are at, our 1s level. So they're at 1 energy and they're moving in like a sphere. And then our next energy, our next electrons are at 2s and they're moving in this sphere, but they're at this energy level. And then our next electrons are moving in this dumbbell patterns at still the second energy level, but this is how they're moving. And so this is kind of what we're trying to talk about, because guys, electrons are so important. Electrons are what does everything in chemistry. I mean, protons and neutrons are also important, but electrons are really what makes chemical bonds and all this stuff. And so our first rule for making these orbital diagrams is the lowest energy orbital are filled before the higher energy orbitals. So this is your Aufbau principle. So this kind of just makes sense. When we are talking about our energy levels, oh man, these circles are terrible. I want to say I blame the computer, but I just don't think I'm very good drawing circles. Okay, so this dot in the middle is your nucleus. So when we're talking about these energy levels, it kind of makes sense to say, yeah, you're going to find electrons, here, and here. You're going to find electrons out here, and then it's going to fill up these energy levels because the pool of the nucleus is positive. These electrons are negative, so these electrons are going to be close to the nucleus. They're not going to want to be like way out here. Oh, this circle is just getting worse. They're going to fill closer to the nucleus before they're way out here. So this graphical representation of where your electrons are is going to show that. So we're not just going to skip this energy level here. So second, each orbital gets 1 electron first before a second electron is added to the orbital. And this is your Hund's rule. No 2 electrons can be put in the same, they're not going to be right next to each other. So I think a good way to think about your Hund's rule is like a bus. And so the electrons are like your passengers on your bus. If you've ever ridden on a city bus, I don't actually know if most of you have. I grew up riding city buses because where I grew up, that was like super normal. Everyone rode city buses. And when you get on the bus, you sit in an empty seat. Like if there's a bunch of empty seats, you're just going to sit in an empty seat. And when someone else gets on the bus, there's this social norm thinking, okay, that person is going to then sit in their empty seat and so on. And you're going to basically sit in the bus where you're not sitting right next to a stranger if you don't have to. If you have to sit next to a stranger, then you go and sit next to them. But until that point, everybody is going to choose to sit separately. They're not going to want to like invade somebody else's personal space if they don't have to. And so that's what's going on here. Again, these electrons, they're negative. They're going to like push against each other. And so they don't want to be super close if they don't have to be. So this is the proper way in which we write it. Because again, we're not just trying to count how many electrons are in an atom. What we're doing is we're trying to talk about where are the electrons and how are they moving, and like how can we best figure out what's going on here. Our third one is only 2 electrons of opposite spins can occupy each orbital. You can only have 2. There can only be 2 electrons. Whoa. So weird. I don't know why there's balloons. I'm guessing the PowerPoint is just as excited as I am about the fact that you can only have two electrons in your orbital. And remember, the sphere, it can only have one orientation, so there can only be two electrons in there. Your dumbbells, it can move in three orientations. So you can have 2, 4, 6. But they have to have opposite spins, and the arrows going up and down represent the opposite spin. Okay, so we are going to actually attempt to draw the electron energy leveled orbital for oxygen. So first, how many electrons does oxygen have? So we need to know how many electrons it has because this whole thing is about electrons. Note, the atomic number is equal to the number of protons. So your atomic number, if you look on your periodic table, it's going to be this number in your top left little corner of each of your elements. And that's the number of protons. And so the number of protons, since it's the number of electrons, as we can say, oxygen has 8 electrons. So we're going to remember or note the 3 rules from from our previous slide and try to draw this diagram. So we're going to start. Each arrow represents 1 electron. So we know oxygen has 8 electrons. So if we're looking here, oxygen is right over here. So something you should note right away, if you remember, is this is your P block. It's like, okay, cool. It's going to be in your P block. So we start all the way at the beginning. We start kind of all the way in our S block. And we're going to move. We're just going to slide our finger right on across. Slide to understand where our electrons are at and what they're doing. So they start in your very first energy level, and they're going to fill in from there. So we have 1, 2. So it's kind of like 1, 2. Okay, that fills up your first energy level. And now we're going to move on to our second energy level. And that's 2s. And so you have an electron at 2s. And then we're moving over. That's another electron here at your 3s. And so we're just following our finger over right here with your 2. So then we hit here. So now we're in the P block. So we're at 2p1. We have 1 electron. And now we're at 2p2. We have 2 electrons. 2p3, 3 electrons. 2p4, 4 electrons. So we have 2, 4, 8. We have 8 electrons. Oxygen has 8. So guys, is that correct? Did I do everything correctly there? Is this what electrons want to do? Do they want to be nice and close? Do they get on the bus and then they immediately sit next to each other even though they're complete strangers and it's really awkward and there's other open spaces? No! You should be having all kinds of red flags. You should be like, bruh, like, you gotta move. This is awkward. It's the Hund's rule. They don't want to be close to each other like that. So when you're drawing these electron orbitals, you have to keep this in mind. So we're gonna do this again, but this time we're gonna do it the right way. So we did 1s, 2s. Let's do 2p. So we have an electron. It wants to be there. Another electron. So that's 4, 6. So we have 6 electrons. We have 2 more electrons left. So we're right here. So 6 and then 7, 8. So we're gonna go 7, 8 electrons. Now these electrons, this is how they're gonna work. They were able to spread out as much as they can. And then with this other electron, when it has to be there, it's going to have this opposite spin. So this is a correct drawing of your energy level orbital for oxygen. And you're just saying, for oxygen, there's 8 electrons. And what we know about those electrons is 2 of them are somewhere in this ball-like pattern in the 1s, like the 1 energy level. And then 6 of them are going to be in this second energy level, in this ball-like pattern, and in this clover, or not clover, but dumbbell pattern as a 2 energy level. So we're going to talk about oxygen. We're just going to kind of look at, we just did this orbital diagram for oxygen. So this is kind of the correct, this is the correct orbital diagram for oxygen. And now we're going to talk about our electron configuration for oxygen. Guys, the orbital diagram and the electron configuration are saying the same thing. It's just 2 different ways to say the same thing. Like one is showing kind of this graph right here, and one is just writing out the numbers. It's the same thing. Like, don't let it freak you out. It's not different. It's the exact same thing. It's just two different ways of saying the same thing. So again, if we look here, we're trying to say, what are our quantum numbers? We start at the beginning. This is 1s, and max capacity, you can have up to 2 electrons. So we say 1s2. Look, we have 1s, and there's 2 electrons. So that fills in, that's all we can do at our 1s level. So we move down. Let's go to our second energy level. Well, we can have 2s. So we have 2s, and we can have a maximum of 2 electrons. And look, a max of 2 electrons. Now, oxygen is way over here, so we're still moving down our table. So we have 2, and we have to follow through all the way to our second. Now we're in our P block. And for oxygen, we have 1, 2, 3, 4, because we count over 4 and we get to oxygen. So that's our energy level is at 2, because we're in the second row. We're in the P block. That's why we have this P. We're in the P block. And oxygen is the 4th in your P block. And so we can have up to 4 electrons. It's just, obviously, these are talking about specific elements, but the design of the table is to help you think about the quantum numbers. So I'm not saying that oxygen is made up of all of these different elements. No, I'm saying is based on where oxygen is in the periodic table, it's helping you understand the numbers. And if you don't understand those numbers, you can also look at these orbital diagrams and write it from there, because you have 1s2, 2s2, 2p, 1, 2, 3, 4, 2p4. Just to make things just a little more fun, is you have your noble gas electron configuration. And what your noble gas configuration is talking about, these elements in your 8th or 18th, these elements all the way here at the end. Helium, neon, argon, krypton, xenon, and so on and so forth. These guys are noble gases. That means they're noble because they're completely unreactive with anything. They you could put them next to anything. They're like, nah, don't care. And so these noble gases, for oxygen, we just found oxygen's electron configuration. And so we started all the way over here. And we went all the way across, and we said, okay, that's 1s2, and then we started here, that's 2s2, and then we said, okay, and this is 2p. And so instead of doing that, we could say, all right, let's start at helium, and we put it in brackets like this. Okay. We put it in brackets, and then we say, we start here, and then we move straight to our next row. And we say, okay, then we can do 2s2 and then 2p4. Now, for oxygen, it kind of is useless because that literally didn't save us any time whatsoever. But what if you had to find or write out the entire electron configuration for lead? That means you would have to start all the way up here and work your way all the way down across all the periodic table. Or if you're doing the noble gas configuration, you could just write xenon in brackets. So we could say xenon. Oh man, that is rough. We could put our brackets around it. And then we could come down, okay, to our next row, which is right here. And that is your 6th energy level. So then we can start at 6s2. And then we can, finish our configuration from there. Oh dear, that arrow is awful. We can finish from there. So 6s2, 5d10, 2p2. And that's way easier than having to start all the way at 1s2, 2s2, 2p6. So it's just like a shortcut method. All right. We take heart. Everything we just talked about, it really does get easier with practice and with just familiarity with this. Just spend time with this. Spend time just staring at it and trying to understand what is it talking about, because it really is the best cheat sheet ever. You just have to know how to use the cheat sheet. It's like getting a cheat sheet, but it's all in Latin. So once you don't know Latin, You'll be good. So it's just you just kind of gotta figure it out. So we're gonna practice more of those problems. But I want you to just kind of like, whew, we're gonna take a pause from talking about all these, orbital diagrams and stuff, and I think we're gonna talk about stuff that's just a little bit easier to grasp. So we're back to our really fun picture uh, in fashion. And we're going to talk about this last part that I said we were going to get back to is our valence electrons. So valence electrons right here. So our valence electrons are going to be our outermost clothing layer. So in the case of these, models, their outermost clothing layer is there's these jackets. And for this guy, it's his shirt. And so the outermost clothing layer is what most readily reacts with the environment because it's on the outside. If you want to change anything about your outfit, you have to take off or put on your outermost layer first. Like you can't just like take out your organs. Like we're not talking about your protons and neutrons. We're talking about these outermost clothing layer. Those are going to be your valence electrons. So your valence electrons are found in your outermost shell, again, your outermost clothing layer, and it takes part in chemical reactions because these are the ones that are available. These are the ones that are going to react. So when we've been talking about our periodic table, when we've been talking about, our S block, our P block, our D block, our F block, the S and P blocks, so I'll write it on here. This is your S block right here. Your S block and your P block are going to be what we're talking about when we talk about valence electrons, the electrons that are always going to be on the outside. And the reason this is because remember, your D and your F, they're always actually at a lower energy level, meaning your S and your P are always going to be on your outermost energy level. Like D and F, like they're not going to be on the outside. So we're just not even going to talk about D and F electrons when we're talking about valence electrons. So with S and P, these are going to have your valence electrons, and you can have up to 8 valence electrons because you can have two electrons in your S level and 6 in your P. Man, this is really hard to like make my hands stay in the camera. 6 plus 2 is 8. Like this all flows together. You can have 8 electrons in your valence shell because S and P are going to be on your outside. So with these, for this periodic table, it doesn't actually have 1, 2, 3, 4, 5, 6, 7, 8 A like on the top. It just goes 1, 2, then 3, 4, 5, 6, 7, and goes all the way to 18. But what you can think about is just as 1 and 2, and then this says 13, 14, 15, 16, 17, 18, just minus 10. So it's like 1, 2, and then 3, 4, 5, 6, 7, 8, meaning those are the number of valence electrons you can have. So for your valence electrons, how you can represent the electrons, saying, okay, these are the electrons that are on the outside. I'm going to draw this little dot. So we're looking at hydrogen right here, and we can draw a dot. And then if we move across, we say, okay, helium is so like, it's always kind of annoying. Helium is actually thought of as, kind of like over here. Even though it's a noble gas, it can have up to 2 electrons. So let's look at our second row because our first row is a little confusing. Lithium has 1 electron. Beryllium, in your second column, it's got 2 electrons. Third, you have 3 for boron, 4 for carbon, 5 for nitrogen, 6 for oxygen. Guys, like, are you seeing the pattern? Like every single element in this 3 group is going to have 3 valence electrons. Every single element in your 4 group is going to have 4 valence electrons. Every single element in your 5th group is going to have 5 valence electrons. Again, your periodic table, you need to have this. You need to be familiar with what it's talking about. And so we're going to look at how to draw your electron dot diagram. So you find your element. This one is chlorine. We found chlorine, and we said, okay, it has 7 valence electrons. So we're going to draw 7 dots to represent its outermost electrons, these outermost electrons. Now, when you draw a dot, it's just like the bus principle. Like if you're filling in this empty bus with total strangers, everyone is going to choose to sit in an empty seat before any stranger is going to choose to sit right next to them. At least they should. So we're going to have 1, and then we're going to kind of sit over here. We're going to be kind of far apart. 1, 2, And then we're going to draw this dot, 3, and then 4, and it's like, oh, all the seats are taken. Now we have to actually sit next to somebody else. So we'll sit over here, and then we'll draw this dot here and here. And this shows 7 valence electrons. There is not a uniform standardized way that we don't all go right, left, up, down, right, left, up, down, or up, down, left, right. But what we all do is we say we're not just going to draw 2 electrons next to each other if they can't, if there's open space somewhere else. So I like to go, up, down, right, left, up, down, right, left. All right, those Lewis dots, we'll practice those more. We are going to talk about just some simple things here, or more like definitions. I mean, atomic number versus mass number. So for your element, you have your atomic number, and this is written in kind of like how you write out isotopes. Atomic number is your number of protons. And so on your periodic tables, your atomic number is going to be that number in your top left corner. That's your number of protons. And your whole periodic table is arranged based on the number of protons you have. 1, 2, 3, 4, 5, 6, 7, 8, 9, so on and so forth. And then your mass number is going to be the number of protons your specific element has, which you already know, plus the number of neutrons it has. How we measure the mass of an atom is using the Unified Atomic Mass Unit, AMUs, and that is just 1/12 of a carbon atom, or it's 1.66 times 10 to the negative 24 grams, which is an extremely small number. An isotope. This is going to talk about our protons and neutrons. So an isotope, it's the exact same atom. It has all the same number of protons, so it's chemically acts the same, but it has a different number of neutrons. And this just naturally occurs in nature. You'll find different elements and they'll just have varying numbers of neutrons, but they're still the same element because they have the exact same number of protons. And so you'll see the difference represented in the mass numbers. So you can notice the different mass numbers. For lithium, it's saying we have 6, 7, 8. That means we have, 3 neutrons because we have 3 protons. We have 4 neutrons here because we have 3 protons, and we have 5 neutrons here because we have 3 protons. So this, just understanding that isotopes exist is important, because if you look at your periodic table, again, everything comes back to this bad boy. If you look under your elements, you're going to see a number on here. And if you look at the number, none of those numbers is going to be a nice whole number. They're written to like decimal points. They've got significant figures on them. And it's like, okay, well, why are none of them nice and whole? Other than, none of them are nice and whole. And that's because isotopes exist. Like, again, if we could just make chemistry simple, that would be awesome. But we can't, because nature is not simple. And so these isotopes, they exist. And so a mass number, we can talk about a mass number for a single atom as just counting its neutrons. It's like, okay, well, boron, in this case, boron has 6 neutrons and 5 protons. So for the single atom, this is boron 11. The atomic mass, aka the atomic weight, is going to be your accounting for all the types of boron out there. So you have boron 10, which occurs 19.19% of the time in nature, and then you have boron 11, which occurs 80.09% in nature. So boron 11 is way more abundant in nature, but you still have to account for boron 10. And so the atomic weight, they just take the its mass number, and they multiply its specific mass number by the decimal of its abundance. They turned the percentage into a decimal. They multiply that, and then they find your average atomic weight. And that's just where that number comes from. And then finally, guys, what is an ion? An ion is an atom or molecule with a net electric charge, which just means everything on your periodic table, when you're looking at these elements, you can assume they're neutral. They have the exact same number of protons as electrons. That's just what we assume. Now, when the when the atom, when it gains an electron, it's called an anion. And that's because it becomes more negative, because electrons are negative. So now there is more negative charge than there is positive charge from the nucleus. So now you have this negatively charged lithium ion. And if you lose an electron, right here, you've lost an electron because you went from 3 electrons to 2 electrons, you actually become more positive because the nucleus, we'll put a big plus sign here, is positive, and it lost one of those negative charges which kept it neutral. So that's called a cation. I like to think about it like cats. Cats make people happy. They're just positive. Uh, but you can remember that however you want to. And that, my friends, is the end of this PowerPoint.